Okay, so welcome everybody on the 26th Data Science Leuven meetup. Just like last month, it's not an actual physical meetup, but because of obvious reasons, it's going to be live streamed, this time through YouTube. Thank you, Chris, for taking care of all the technical stuff. What do we have on the program tonight? Well, we will start off with Bart de Ketelaere of the University of Leuven, Division of Mechatronics, Biostatistics and Sensors. That's what I read on LinkedIn. I don't know what mechatronics is, but I'm sure it's interesting stuff. And he will talk about big data in agriculture and what challenges and opportunities we have in that area. The second speaker will be Tom Stock, who is a customer advisor at SAS, and he will talk about network analysis for data preparation. And last but not least, we have somebody from Colruyt, and some of you who were on the meetup a couple of months ago will remember that Hendrik Doosterling from RoboVision had a presentation about automatic fruit and vegetable recognition using AI, which I believe was an experiment done at Colruyt, but now we actually have somebody from Colruyt Group itself, and it's Loden Nachtegaal, who is a data scientist at Colruyt, and he will talk about explaining your clusters to business using Altair and SHAP. And not SHAP values, that's what I have understood. Okay, so before I give the word to Bart, these are the usual, let's say, usual reminder of the team who is taking care of Data Science Leuven, our Twitter handles, etc., etc. You can contact us in all these different ways except for face-to-face, which does not work for the moment. But I'm sure if you have something important to tell us, it will get through us some way or the other. There's only a small number of other activities that I'm aware of, because I don't know to what extent Data Science Ghent and Data Science Leuven are doing these days. Maybe I should have checked, I didn't. But what I can tell you is that there is this weekend, or actually as of Friday, I believe, a very large hackathon organized by the European Commission. For those of you who have time to spare in the weekend, I think it's a very big one. A few thousand people will work on this during the weekend. The other thing that I wanted to share with you is, as you might have seen, there are quite a lot of people who are working on the whole Corona issues. And there are a couple of data scientists who are working in that area as well. Or sometimes people will ask, do you know a data scientist who can help us? And one of the people who is looking for additional people who can help them out is Lise Raas. I think she's from the Leuven area, actually. And she's looking for somebody who can help them with analyzing the results of a survey that they have been doing. So if you're interested in that, check out the Twitter account of Lisa. And the other type of help that she's looking for is somebody who can work with MATLAB to migrate the model that they are currently using. Then the next meetup, the 27th meetup, will be on the 12th of May. That's a Tuesday. In all likelihood, this will be another live stream version. We don't know yet in what form that will be, but we will give you the details in due time. And I think with that, I'll give the word and the presentation to to Bart. Bart, the floor is yours.
Thank you, Istvan, for the introduction. And I think you should stop presenting so that I can start presenting.
Voila, that's exactly what I was planning to do. Okay, now I think you need to present, and I will mute myself.
Okay, so I'm starting up the presentation. I hope everyone can see it.
Yes, we can.
Istvan, thank you for the introduction, and also thank you everyone related to the organization of those data science meetup. It's a very nice initiative, and I'm thankful to be able to present part of what we are doing in our lab. So, as the title says, it will be about big data and agriculture, opportunities and challenges. And in fact, I've split the presentation into, let's say, two big blocks. The first block will be the kind of generic block about big data and its role in agriculture. And the second block, which is the biggest block, will be about a specific case study we are currently running in the lab. So, starting off with the first block, the generic thing, what you see here in this old picture, in fact, is an old dairy farmer, and he's busy with probably the most important part of his job, being milking the cows. So it's a kind of time-consuming thing. And because it's time-consuming, in fact, at that time, those farmers had only about 10 or some tens of cows, not more than that. But the fact that it was time-consuming was for them also an advantage, in a sense that they interacted quite often with the animals, so that if there was a problem with the animal, they would recognize it quite soon. Now, if you look at the situation to date, well, a dairy farm looks completely different than what you see here in the picture. Actually, what it looked like is more like this. So instead of the farmer himself or herself milking the cows, there is now a robotic system that does the job. So it's kind of efficient. And because this high efficiency, typical farms now don't have about 10 or tens of animals, but it's more like hundreds of animals. So that's a big difference. And of course, one of the difficult aspects that kind of disappeared, let's say, is the fact that the farmer doesn't spend too much time anymore with the animals. So that means also that those robotics is not the only part of a solution here. But instead of only having the robotics, it's important to also have the right sensors, so that those sensors can sense, in fact, whether the animals are doing okay or not. And that's what you see in the table, let's say, on the lower half of the screen now. All the cows have individual tags, and because they have individual tags, the robot is recognizing them, so that for every time the cow is visiting the robot, you can record individual data for that cow. And that's of course interesting, because if you have the sensors and the data, you can do something with this data to be able to manage the whole dairy farm. So when we compare it to 60, 70 years ago, things have changed quite a lot. And it's not only the case, let's say, in animal farming, but exactly the same happens also with crop farming. So the amount of manual work has been removed, and both for fertilization, harvesting, and so on, it's all done by machines, by robotics, having the right sensors to see what's happening on the field or in stable. So that's kind of the clear trend that we see. So there's a lot of robotics coming in, replacing the manual labor-intensive work, which has the advantage of being very time efficient, but which has also the big disadvantage that the farmers do spend less time with the animals and in the fields. So that's where the sensors kick in to replace, in fact, the human perception by sensing the state of the animals or the fields. And that's what this talk is all about. So those sensors alone is not enough, of course. They give a lot of data to us. Those data can then be used to gain information about what's happening. So that's like the global trend. So because of these global trends, there are kind of opportunities here. So when we look, of course, at the agri sector, or even the agri-food sector, when you look at it from an Industry 4.0 point of view, well, I think it lags behind when you compare it to industries like automotive and semiconductor. But things are quite moving now, and since the industry is quite large, we see that a lot of large players are stepping into this data science approach. And I think one of the first proofs about 7 years ago, I think, was this news that Monsanto, so quite a large agro-business company, which is now part of Bayer, they acquired, in fact, the big data company, the Climate Corporation, for about €1 billion. But more recently, and also much closer to us, let's say, to Leuven and to what we are doing, is also the news of about 1.5 years ago that the German company Evonik has acquired the big data software provider Porphyro, which was in fact a spin-off company from our lab. And that was kind of a nice thing to see, because Evonik, what they do mainly, or a part of Evonik, is providing, let's say, ingredients and additives to the feed industry, but of course they want to have feedback on how good that is doing. So that's the link to Porphyro, which is operating, in fact, a big data platform that monitors animals and give early warnings. So that means that things are moving quite rapidly in the agricultural sector, and that gives a lot of opportunities to data scientists. And maybe before I come to the real application I wanted to talk about, it's also important to tell something about one of the main challenges which makes this sector probably a bit different from other sectors, is the fact that you have biological variability about everywhere. So that means that every animal, every crop, every field is just unique. And being unique, it's also often more difficult to define exactly what's good or bad. So a cow giving 25 liters of milk a day, is she doing good or bad? Well, that's not so easy to say, because each individual cow is different. So we should compare her probably with herself and not with some peers. So it's not that easy to have this biological variability. But this biological variability comes from one side, let's say, as a kind of an input. But on the other side of the spectrum, we have the consumers. And what the consumers, in fact, want, those consumers, in fact, want most often a kind of a more constant product quality. So from the different perspectives, let's say, there are quite some challenges in the agricultural sector, and those need to be taken into account when you approach it through the data science. And what I will start doing now is I will be talking about one very interesting, I find, case study we are running today, let's say, in the lab. And it's all about the monitoring of insects. So insects, they're quite important in the agricultural sector, and it's for many reasons, in fact. You have the pest insects, so the insects we don't want to have because they are sources of crop losses, for instance. But you also have beneficial insects which you want to have, for instance, for pollination of trees and flowers and so on. So having some information on whether there are pest insects in the field or how many beneficial insects there are is quite important to agriculture. But as we all know, I guess, is that also in human applications, the spread of diseases is most often also done by mosquitoes, for instance. If you look into malaria or Zika and the like, well, those are spread by insects as well. So also for those applications, having a very clear idea on the presence or absence of certain insects is an important thing. And we see also during the last years that the interest in monitoring insects has increased quite rapidly. And that's mainly also because of global trade and global travel. So because we trade fruits and vegetables from all over the world, we import a lot of foreign insects. And having a grip on whether those are present or not is important to know. So that's like the setting. Insect monitoring is an important part. But when we then look at how this is happening today, so it's not like 20, 30 years ago, but it's still the practice of today, is that it's still a very manual work to do. So what you see here at the right side is what we call a sticky plate. And a sticky plate is literally what the name says. It's a plate, it's a piece of plastic that is put into the fields. It has a color which attracts insects, and the surface is covered with glue, so that insects get trapped on it, and that afterwards the plates can be collected and the number of insects of the different kinds can be counted by people that are specialized in doing so. So I think it's clear that this is kind of a labor-intensive way of monitoring insects. You should install the traps, you should collect them, you should be manually counting the insects, you should be identifying which kinds of insects are on the plates. So because of the fact that it's time-intensive, it means that it's only done on a very low resolution base. And I mean with that, well, you typically do that only one time a week. So if you collect the plates and one day later the insects invade your field, you probably will know it only 1 week later. And the same holds for the resolution in space. You only do it for a few fields, let's say, in a certain region. So it's not an ideal thing, and what people are asking for are automated procedures. And when you want to devise such automated procedures, we need the sensors and we need the data analytics. So I will focus on the data analytics part, not so much on the sensor part, but I have, I think, 1 or 2 slides that explain a bit about the sensor, because it's important to understand what we did with the data later. So the principle of the sensor is very easy. So what you have here on top, it's a light source. So it's an LED, for instance, so it's providing light. And at the bottom here, you have a light collector, let's say. So the more light that falls on the light collector, the more electricity it will generate. So logically, if an insect moves in between the light source and the collector, it projects a small shadow on the surface here, and the amount of electricity that is generated will be lower. But it's not only the shadow, let's say, of the insect when it moves through the sensor, but what we saw also is that the position of the wings is also kind of important. When the wings are exactly horizontal, the shadow that is projected is much larger than when the wings move up or when move down. And that's interesting to know. So that means that we can have an indication of what we call the wing beats, meaning how fast and in which way the wings of the insects are moving up and downwards. When you will look at the typical signal, it looks like this. So each time the insect flaps with the wings, you see a kind of periodical pattern going up and down. And those are the kind of data which we want to use to identify which kind of insect flies within the sensor. So that's a generic, let's say, background around the sensor. So the sensor is quite small, you see it here. So what we did first in the lab, we have a small cage. We can release insects so that they can fly in the cage and fly through the sensor. And what we typically do is we put, let's say, around 50 insects of the same type at a time. And then we record all signals of those 50 insects and we store it on disk. And afterwards, we can do that for multiple insect types. When we do that, in the end, we have quite a large enriched data set. So the data set that I will discuss here, it's in fact a data set that consists of 2 different types, let's say. There is a smaller data set part, which is about flies. And there is a very big data set which is related to mosquitoes. So the mosquito data set is around 280,000 signals. And those signals come from 6 different classes. But the 6 different classes are divided in 3 different, let's say, genus of mosquitoes. So those 2 are of the same genus. So those are Aedes mosquitoes. The 2 following ones are Culex, and then you have Anopheles. And the first 2 ones are important because they're related to Zika. The last 2 ones are related to malaria, and those are more the regular mosquitoes we see at home. So, but you have 6 classes of mosquitoes, and then you have 4 different classes of flies, of which the 3 first ones are kind of fruit flies, The last one is a rather local fly to the Belgian industry, let's say. It's mining into the roots of chicory pines. So that are the signals that we will have to classify. So the hypothesis is that the wing beat we have is providing enough information to discriminate between the different kinds of insects. What I show here again is a time signal. So you have to think about a time signal of about 600 milliseconds. When I zoom in, it's a type of signal I showed before, where you exactly see here the strokes of the wings. So that's a time signal. But we can use a time signal, but because of the periodicity, we can also look at the frequency content of it. So it's a power spectral density I show here, which shows how much energy in each of the frequencies is present in a certain time signal here. So we could use a time signal, but also we could use a kind of a derivative of it. Now, you could also combine both worlds in the sense that you can keep the time aspect, but you can add the frequency aspect as well. And that's what you do in a spectrogram. So you can look at this as a kind of an image in which for each time instant, you see which frequencies are dominantly present in the signal. So we can also use this kind of a signal as a derivative of the original. So that's what we did. And actually we did quite a lot of different things with the signals. But what I will discuss today is only the use of the raw signal and of this spectrogram. We did a lot of different approaches to it, of feature extraction, reduction of dimensionality, and also kind of different classifiers. But I will just restrict myself to the complete raw signal fed into a one-dimensional convolutionary neural network. And for the spectrogram, it goes just as a whole, let's say, as a kind of an image to the convolutionary neural network. And I will forget about also the septal analysis and other things we tried. So I only discuss those two aspects to give an idea of what those kinds of sensor technology could mean. So that's just summarized here. We have the sensor, we have the electronics, we have both the raw signal that we feed into CNN, and we have then the 2D signal that we feed in the 2D CNN to make our class predictions. So this is what comes out of it. So you see here that the confusion matrix for the fly data sets. And yeah, well, what you see first, of course, is that it's kind of performing well. So the accuracy we have is around 97 to 98%, depending on how you define the accuracy. So that's quite high. So we are quite happy with that. And we saw that both the raw signal as well as the spectrogram performed quite good. So it's with accuracies of above 98%. So for the different kind of fruit flies and for the other type of fly, this kind of sensor seems to pick up what we need. When we then look at a bigger data set of the mosquitoes, we see a similar thing. So we have accuracies of above 90%, which is, well, I should say even higher than what we thought of. And both the raw signal as the spectrogram are doing quite okay. But when we looked closer to those confusion matrices, what we saw is that in fact, we knew that we had two Ides species, which are very similar to each other and which were much more different to the Anopheles and to the Culex. We saw that still the CNN seemed to be able to discriminate the two ones here. And that was kind of, well, let's say strange, because we really expected that those misclassification numbers would be much higher than a misclassification you would have here. So we went further looking into the data, and in fact, an attention point, and I think it's an attention point for everything we do in classification in general, is that the way you validate such things is extremely important. And of course, what we had here is because we release about 50 insects at once in the cage. Well, one insect can be traveling through the sensor multiple times. Also, two insects can go at once through the sensor, but mainly one insect can generate multiple times. And when one insect is passing the sensor multiple times, we should in fact be very careful in how we validate a thing. So we have the classical training, validation, and test procedure that we do. But if we don't make sure that the same insect appears in training, validation, and testing, when we don't take that into account very well, we might be generating, let's say, over-optimistic things. So what we feel for now, so it's still ongoing research we are doing here, is that the results we show here are probably too optimistic, and that we should, well, let's say, advocate to split the data set more on, let's say, stringent rules we should impose there. So this is something which is extremely important, but when we look at publications, I think it doesn't deserve enough attention to make really the test set more independent from what you do in training and validation. So that's for sure a thing which requires more attention. So that's kind of the work in progress. And what's in progress as well is what I showed was models which were trained, let's say, de novo, so from scratch. And we're also comparing the pre-trained networks to the de novo trained models, and related to that also the whole concept of transfer learning. And the transfer learning is something which is kind of interesting in this application, because what we're interested in as well is to automatically detect when a new class of insects kind of invades the place. And when this is the case, you want to kind of update your classifier to include also the new test insects. And this is something we can incorporate as well. And as I said also, the important part of the work in progress is also to look at the accuracies and the capabilities of those nets, depending on the way you validate it. So the PhD student who is working on this, so Yanis Kalfas, is momentarily, he's looking into the different validation aspects and how this is influencing the results we. So that's the end of the application I want to share with you. So when I just conclude here, there were 3 main points, let's say. So I'm quite convinced that, well, agriculture is of course a very large field, and I think it's a very challenging field for people that are busy with data analytics. So I think it's really challenging to look into it more. But we see that in that sense, for automation and the introduction of new sensors goes quite rapidly. So I expect it to be kind of explosive in the years to come. So the amount of data we will gather from that sector will increase as well. And when we then look at our first results based on the deep nets that we used, is that everything is kind of encouraging, but that we are kind of skeptical, let's say, about some classical ways of validation, and that we are diving deeper into that aspect right now. So with that, I come to the end of my presentation. So you see some acknowledgements here of different partners in the project and financing. So I thank all the instances and people that I mentioned also here on the slides. And I thank also all of you for listening to the talk. If there are any questions, I will try to answer. So thank you for that.
Thank you, Bart, for this very interesting presentation. And normally there's a big applause, but we cannot do that here. So you have to do congratulations, unfortunately. So for the people who are watching on YouTube, if you have a question, please type them in the message box and we will read them out loud. There's a small delay between what they see and what we have, so we'll give them some time to type it in. In the meantime, I don't really have a technical question, Bart, but what I was wondering, it's not clear to me. I mean, let me put it differently. In the beginning of your presentation, you explained to us that, let's say, agriculture has changed a lot because of technological changes, etc., etc. And I was wondering, to what extent do you see that in the education? I mean, people who are doing this type of research, are they typically sitting in the bioengineering departments, or how should I see that?
It comes from both sides, I think. So you have the direction of people in data science that move into agriculture, let's say, as a new application field. So this is for sure. But what you also see is that in the whole bioscience engineering education, that there is of course more and more focus also on sensor technologies and data analytics to do something with it in that sector. So I think somewhere it converges. And that's what you also see in companies which are busy in data analytics for the agricultural sector. If I take the company Porfirio, for instance, as an example, they're doing big data for the poultry industry mainly. So the people that work there come both from the bioscience engineering, because I'm still convinced that the background or the deep knowledge about the systems you work with, in this case, animals you work with and the signals you get from it, that's an important point that you should not forget. But also in the same company, you have people that have, let's say, historically nothing to do with agriculture, but are very good in data analytics. So I think it all comes together, let's say, there. But as I said, it comes from the both sides, from the bioscience education, which is changing according to what we see in practice, as well as data scientists who look more and more into these applications.
Okay, great. So now let's have a look at the questions. Let me see if I can show that here.
If you want, I can read them, Istvan.
Yeah, go ahead, Chris.
Yeah, all right. So, well, Lode has a question, and it says, Bart, is the accuracy that you described of the classifiers, is it in sample or out of sample accuracy?
What do you mean with in of out of sample accuracy?
Well, Lode is in the call, so maybe he can ask the question directly. Lode, if you unmute yourself.
In sample, you means that you use all the samples for training as for validation, and auto samples that you split. Actually, you answered the question in the slide after I posted the question. So
okay,
indeed, I think the accuracies that you were showing there were in sample, so not with the test validation split, and that you have to still work that out to have more realistic versions.
I think it's a bit different here. So you would call it auto sample in a sense that the test set is kept apart and the results I show here are based on the test set. But the difficulty, which is, or I think the quirk that came up here is that in splitting the data from training to test set, let's say, because we have the several insects in one cage, it can be the case that the same insect provided a signal in the training set as well as a signal in the test set. And that's probably where the team comes in, that it's not as independent as we should have it probably.
Okay.
All right.
Thank you.
Okay, Chris, are there any other questions?
Yes. Jennifer Roelens asks, how do you think the application will perform in the field with different weather circumstances, a mixture of insects, for example?
So the first part was about weather, and the second one was about the mixture of insects, right?
Yes, I think so. That's what it says. Yeah.
Yeah. So the weather thing, well, that comes down to mostly of part of the electronics which have been worked on. So we have an artificial light source. So it's a light source and the detector, which is kind of constant, let's say. So that removes part of the difference you have in weather conditions. I must say that weather conditions do come into play because the behavior of the insects can be different depending on temperature, for instance, and humidity. But the sensor includes also temperature and humidity as a feature. So in that sense, let's say it's kind of covered. The second part is a very intriguing part because here we know exactly which kind of insects we put into it and we built the classifier to detect those. But the other part of the research we are doing is, well, to see also the insects that have not a high probability of belonging to the classes we see. Well, to detect also that those are coming in so that we can update the classifier for new species that would come in. I hope that answers the question.
Yeah, it makes sense to me.
Because of the delay, we will know it only a bit later. Yeah.
Chris, unless you have a very urgent question, shall we go to the next speaker?
Yeah. So those were the questions. There were just a few people, Bart, just for you to know, that really liked your case, and thanks for presenting it. Yeah.
Well, thank you all, I think, for being present. And if you have extra questions, you will find my coordinates. You can always contact me.
Awesome.
So thank you very much.
Thank you very
Okay,
much.
so
Bart.
thank you, Bart. Thank you, Bart, for this. And now I think you need to stop presenting. And now it's Tom from SAS, and we've already had, I think, some people from SAS presenting. And this time, Tom will talk to us about network analysis for data preparation, which is a title which intrigues me. So I'm looking forward to this talk. Tom, the floor is yours.
Yeah, thank you very much. Thank you very much for the opportunity to present. I'm not sure the title is very well chosen, but it's how it is. It's a bit difficult to pass after Bart. There's a very articulate presentation, very interesting. So I am Tom Stock. I work for SAS. SAS is a software company, software that is dealing with data analytics. I've been working mostly for government organizations and specifically to a certain extent in the field of public security. So those agencies from the government that protect our borders, that protect our people, like the military, like the border guards, like the police, and so on. And so network analysis is indeed very important to them. But the point I want to make today is mostly that network analytics is not only about visualization, and network analytics carry a lot more. And I want to articulate that point in my presentation. So first of all, what is data preparation? I mean, in an organization, you're very familiar with the fact that most organizations are building data warehouse, and this is not stopping now with data lakes. Data warehouses are still critical. You need in any organization to bring your different data together, your different operational data from your ticketing system, from your customer management system, from your production lines. And all this data is put together, and the result of this is usually star schema. And there's a lot of advantage to that, efficient storage, fast retrieval, and it creates flat files that are used for business intelligence. So that's how you take your decisions, that's how you drive your company, and this is not going to stop. But now, if you've been working in data analytics, you know that it's not enough. And what we do in data analytics is we use analytical tables, and those are different. Usually they have a different granularity. The granularity is going to be at the level of the analysis. So whether it's about the customer, whether it's about the citizen, whether it's about a product, you're going to have a record-based table. And this table is going to be as wide as possible. Usually you're going to try to have a very wide table because the features that are going to be picked up by the model must be the most predictive, the one that carries the most information. And so whether you have, I don't know, in the field of public security, committed enough funds in the last year, the last 3 years, last 5 years, last 10 years, may carry a different predictive behavior of whether you're going to commit a second offense. And so this process of building all these features is very important. It's very iterative and is schemaless. So it's a bit different, but the data warehouse and the analytical base table are both very important for an organization. And network analysis can actually play a role in building those abilities. To explain my case, to make my case, I will use one project. One project we have worked on as an organization because we have actually people who are specialized in public security and they work mostly on that type of projects. And so this project actually started with data collection as from November 2015. After actually the terrorist attacks that occurred in Paris at the time. And so as you see, this data collection process was actually quite manual as well. So it was about trying to find out what happened. Who are the different people who actually took place, who actually were part of the criminal organizations, where they've been, when, with who, and so on and so on. And so that data collection process, as you see, was actually trying to find out what was happening, as we are not specialists. We were not involved in the cases before. And so the objective was actually to take that information, which is quite raw, which is quite linear, and to make sense out of it. And so to build a network that would actually allow us to understand who are the most important pieces in that puzzle. And so I will explain and I will show you the results of that investigation after a bit of theory. What is the theory behind? So network analytics actually rely on a key process which is called entity resolution. And what is entity resolution? Well, it is basically that you start with a table, typically a table you would find at the entry of your data warehouse, which is containing all the information, but records per records, event per event. And in these cases, you see on the left-hand side, I've taken examples that you may have heard of. On the right-hand side, it's just generic data. But the point is that if you would actually display that as a network, you will understand immediately that this network is actually too big for the information that it contains. You have 2 times the same protagonist on the left and 3 times the same protagonist on the right. Now you see that they are connected. They have used the same computer, they have been seen or they've been living at the same address, but you understand very quickly that there is something to do with this data, especially if you're familiar with data science. And what do we have to do with this data? Well, we have to actually do entity resolution. On the left-hand side, it's fairly easy because the person across the different records, the different data we have, is the same name, and we even have a passport number that is actually confirming that. So it's very easy to resolve that entity and aggregate the information about this person. On the right-hand side, it's much more complicated. It requires actually 2 different technologies that are part of this entity resolution process. One is the quality knowledge base, and the other one is fuzzy matching. The quality knowledge base will allow us to actually use linguistic rules, use knowledge that has been built in the organization, a taxonomy, to actually know that 2 names are actually the same person. Fuzzy matching will allow us actually to match with, for example, different languages which would actually, translation would not be exactly the same. So the fuzzy matching will allow us to match 2 records that are 95, or 2 persons that are 95% the same, or 90% the same. And we establish those rules based on training and iteration and also expert knowledge. But the result of this is very important because we change from something that was relatively rich to something that is more simple to interpret. And we don't lose, or we lose limited information through that process, but it allows us to have something more clear, how those 2 people are connected, who are those 2 people, and more important than that, now you see the table below that starts looking much more like the table we would want to feed into a machine learning model. This is the kind of table that is actually more filled. There is much less missing values that can be actually fed into a machine learning model, from a logistic regression to a deep neural network, whatever. But this is already a better table to work with, and this is called entity resolution. So what are the results? So you've seen all the different data records that we were actually first manually recording, and then we put it in a data set, and then we actually applied this entity resolution process to that data set iteratively. So every day we would collect more data, or not every day, we were not the investigators themselves, but we were passionate about the case. So we added data and we ran this entity resolution process. And so we reached something like this. Well, we actually reached this. We started the collection process on November 13th, well, a few days later. And actually, this was the status of the network on March 18th. So this was all the information we collected about the event that occurred in Paris. The first thing is that actually this event in Paris brought up a lot of information about the past. And it allowed us actually in our network to identify what is called the Verviers cell. What is the Verviers cell? This is actually an anti-terrorist action that happened in Belgium a few days before this group of people were about to attack a police station in Verviers. And this case is very specific, very important to me because I come from Verviers actually, and it happened in the same street where I would wait for my parents after school. And so this was quite interesting. So it brought back a lot of interesting past information, and it's also allowed us to identify a second part of the network, which is called the returning cell. And in the returning cell, you have almost all the people who participated to the attacks of the 13th of November, which involved more than 10 people. And why are they called the returning cell? Is because all those people actually, or I think, yeah, all of them were in Syria. And as foreign fighters, some of them were actually coming from other Middle East countries, but they were all foreign fighters that came back and traveled through Europe and actually committed those attacks. And finally, the last part of the network, the Molenbeek cell. And this we found out on March 18 that there was a strong Molenbeek cell. I mean, this is no surprise to anyone, but that actually committed the terrorist attacks on Brussels airport and in metro on the 22nd of March. Now, the point is not there. Of course, those people, why are they called the Molenbeek cell? Because most of them grew up together actually in Molenbeek. But the point here is actually that network analysis is not only about displaying, it's also about the fact that we can find specific entities in that network. And why is this important? This is because we can automate that. We can automate the calculation of betweenness in those networks. And the betweenness is going to tell us who is the person who is actually connecting the different parts of the network. And so by targeting the person who is the most central or the most central to the network, you're the most likely to stop the action of the bigger network. And in this case, Najim Lashrawi was the one who was involved in those 3 attacks, and who was also committed the suicide attack at the Brussels airport. And so network analysis allows us, or would allow us to actually focus our attention to the people who actually communicate and ensure that the cell is alive and work together. Now, the table we have created, the result of the table we've created looks like this, okay? But the entity resolution process is more than that. Our objective is to have a wide table. And in this case, we have actually reduced the Y dimension, but we haven't increased that much the X dimension. And so that is very important actually in your entity resolution, to have flexibility to actually add features during that entity resolution process. And for example, typical features that you're looking for when you do entity resolution is features like alias. How many alias is a person using throughout the events? And so in this case, the different numbers of alias can be very predictive. The number of systems in which a person is present, it can be very high, it can be very low. In different cases, this can be actually activating your risk score. Whether a person is an own car or yes or no, that is basic features. But whether there is a car ID address, in public security, this may be very important. If you know that someone has a car ID address, this, even though that may not be yours, it can be flagged and you can be associated with movements. Another very typical feature that is very important to actually use when you perform entity resolution is who is paying for what. if you are doing purchases on the internet, if you are, making a transaction, are you the owner of the payment? And is the owner of the payment in your network? These are very important variables to actually take into account when you're doing that entity resolution process. And so, finally, the next step, and it is that network scoring is not only about adding the risk score of each person in the network, it's also about the shape of the network itself. And so on the left-hand side, this was our first network. And this first network, actually the shape of it cannot be associated with a very high risk score because it doesn't mean much. It's not clean yet. It's basically, you would build a network scoring model on poor quality data. In the middle, you start having something, but of course, the more you get data, the better you can have. And the right-hand side, then you end up with a very good example of a network that should have a very high risk score with different individuals with very high risk score, but also very strong indicators of that shape of networks and historical information, like, for example, the links with the Verviers terrorist attacks. So I think my presentation is a bit shorter than the others, but good for you, but for everyone. It's a sunny day, but main conclusion is that social networks is not only about visualization. It allows us to define entities which result in a cleaner analytical data, which is much more fit for training. Second, by actually applying entity resolution and then applying centrality measures across that network, then we can identify high-risk individuals. In this case, this person, Najim Lashkawi, was probably the person, if we had been able to remove earlier from the population, would probably made the attacks more complicated to synchronize, to organize, and so on. The third point is that it improved your APT by bringing new highly predictive features about those individuals in that network. And so finally, by actually building that entity resolution, building that network, we allow to have data that is sufficient quality, to do network risk scoring. And so then you can identify the groups of people that carry higher risk. And so, yeah, that's my main point, that network visualization is not the only purpose. You can do a lot with network analysis and do much more with your machine learning projects. And so I would like to thank you for your attention. I would like especially to thank Florian Bertrand, my colleagues, and Anthony Severins, colleagues as well, who have both contributed, especially Florian, on the data collection. And yeah, and that's it for me. Thank you very much.
Thank you, Tom, for your presentation. And while Chris is browsing the questions on YouTube, I'm looking at Bart and Lode, whether they have a question for Tom or not. No. Chris, do you have a question?
Yeah, Tom, maybe from my side, or maybe I missed it in the slides, but did you use any specific graph algorithms to build those networks, or was it more manual exploration and connecting the dots?
What do you mean? What did you call them? Cross algorithms?
Graph algorithms. You have, like, I'm definitely not an expert, but you have these algorithms that detect cliques and detect like common groups and stuff like that. And which did you use, and what was your experience there?
Yes. Yeah. So yeah. Of course, as a software company, we have algorithms. And those algorithms are called network entity resolution. It can be real time, or it can be a batch process. And this entity resolution is the one that actually builds the network. And so our graph algorithm are actually the entity resolution algorithms.
Okay, so it was some kind of almost fully automated process that you point the algorithms to your original table, and then it builds the network from that table. It tries to detect the links itself.
Yeah, in this case, the fully automated is a big word because the data collection process was manual, and we didn't do any unstructured data processing.
Yeah. Okay. Cool.
But from the table with the dates, the different events and so on, different people, then yeah, it was automated.
All right.
So Tom, the question that I have is, was this like a one-off kind of a research project, or is this, let's say, is this used in the normal workflow of the police and people who are dealing with this kind of terrorist activities? And if the question the answer on that question is yes, what did you do to make this operationally feasible for them?
Okay. There are several cases where we have made that operational, mostly in the case of money laundering, in the cases of fraud rings or traffickers rings. In the case of terrorism, I was certainly not involved in operational deployments. But yes, we have customers using our software for that kind of purpose.
Right. Okay, good, thank you. Chris, if there are no further questions from our YouTube folks,
no,
there is one.
There is one.
There is one. Okay,
yeah. And even a contentious one. So Tom, I'm looking forward to your answer here. The question comes from a guy or girl named Lackerol Sugar Free. I don't know. And the question is, did using SAS for this analysis bring any added value compared to more modern technologies such as Python or R?
Well, I mean, feel free to do it in Python or R. I mean, but I mean, it is a very different. It's a very different approach. I mean, if you are a Python or R users, I'm sure you can do a network analysis. Now, in the case of government agencies, there is a lot of need for governance. I mean, you may have victim information in your data sets. You may have information that is not to be disclosed to you in your data set. You may need to make sure that there is a strong performance and scalability needs. In the case of AML, for example, there are millions of transactions to scan, and so you need a lot of governance around it. So Python and R can be used at some points in the process, but I think to ensure the governance or the scalability, SAS can provide a lot of help. And in terms of visualization, in this case, I didn't use our visualization tool, but if you want, feel free to check SAS Visual Investigator online, and you will see that it renders a lot better than what you could find when you use Matplot, Lib, or Shiny to build your dashboards. But I fully understand that if it's a one-off exercise, you would have the same experience with SAS as with R or Python, depending on how you code with one of the software or how you know algorithms.
All right, cool. Thanks.
Okay.
There are no further questions.
Sorry?
There are no further questions, so you can go ahead.
Okay, so then thank you, Tom. Thank you once again. And I propose that we now go over to the last of our three speakers for tonight. And that's Lode Nachtegaal, who is a data scientist at Colruyt Group. And well, some of you might know that I work in the market research industry. So I'm absolutely looking forward at a talk which will be discussing clusters and Shapley values. Lode, it's up to you now.
Thank you. So while this is firing up, Okay, so good evening everybody. My name is Lode Nachtergale. At Twitter my handle is cast42. I work at Colruyt Group, and for the next 20 minutes I would like to further deepen your tool belt for using clusters to explain large sets of data to the business. I work at Colruyt Group. I have a team of 25 data scientists and engineers I belong to. We are a quite diverse team. We have 1 out of 5 is female. We have about 7 nationalities, depending on how you count those nationalities, whether they are born or nationalized. And this group of 25 people belongs to the division that is doing business analytics and insights, so which does data insights and reporting, and that's a team of 130 people. But today we will talk about data science, because we are Data Science Leuven. And I know that a lot of you would have some beers after the sessions. Unfortunately, we can't, but to accommodate a bit for that, we go for wine today. And so the data set I want to explore today is a set of 5,000, about 5,000 Portuguese white wines. It's a data set being provided by the university in Irvine in California. And it's an open set which is used a lot. And it looks like a typical retail question I could get. Of course, I won't discuss ticket information of you guys because we take privacy very important, but this is an open data set. So now suppose that business asks to you, okay, here I have 5,000 Portuguese wines. Can you tell me something about that data set? What would you do? First you look out what for information that they give you for each bottle. So here we see a nice Portuguese wine, and for every bottle in those 5,000 lines, we have 12 datas, and 11 of them are chemical characteristics of the wine, like acidity, how many alcohol is there, and so on and so forth. So the question now is, can we group sets of wines together which are more or less similar, such that instead of working at the individual level, we can go up and talk about groups of wine. So before we start that, we first start doing data exploration, and I'm always using Python for that. And I like pandas a lot, and I'm very fond of interactive visualization in Alter, and I will explain a bit about that. So the first thing you do is that with these 3 lines of codes that you can obtain the data, you just specify the URL, you do a pandas read, and you get the data frame, which is summarized here at the bottom of the slide. Here you see for every column, you see how many there are, so 4,080, 98, the mean, the standard deviation, and the quantiles for all the columns. So we know that we have 5,000 lines. So let's try to visualize that, to explore this data, and therefore I will use Alter. Alter is a visualization library, open source, made by Jake van der Plas. Jake van der Plas now works at Google. He wrote also a very good Python data science book, and it's based on a grammar. Other very well-known libraries for visualization are ggplot. ggplot is also based on a visualization grammar, and it's probably one of the reasons ggplot is so popular for making visualization. In the Python world, we have now Alter, which is similar to ggplot, like Python is similar to R, at least according to Jake van der Plas. If you want to know more about Alter, there is a good explanation by Ethan Lees. It's here. He explains that Alter builds on Vega, and Vega builds on D3, which is the same visualization engine like being used in Tableau. And if you want to get started with Alter, I recommend you to look to a page made by Vincent Warmerdam on calmcode.io, where he explains with videos how you can make Alter visualization. Now, instead of talking about it, let's do it. Here is some simple code that says how to make a graph. You say you take your data frame, And from that data frame, you functionally apply functions to that data to produce this, this graph. So you say, okay, from this data frame, I want to put points. And where do I want to put points? Well, on the x-axis, I want to have the fixed acidity. And on the y-axis, I want to have the volatile acidity. And every dot that you put here, I want it to have it a color, and the color is the quality of the wine, which is a number. By just this line, you produce this graph, and that's nothing spectacular. It looks good. It's D3 quality. It looks like it came from Tableau. But the nice thing about Altair is that with just adding 2 lines, you add tooltip alcohol and a dot interactive, and this graph becomes interactive, which I will demonstrate now. So I will make a live demo. If that goes well, bear with me. So here is the graph generated by the first line, which is not interactive, but by just adding tooltip interactive, I get this graph, and you see I can hover over it, and I get the tooltip, which is the quality of each wine and the alcohol, and I can zoom in, and I really can go at the level, or I can pan to the left or the right. So that's very easy to do. Okay. Now, of course, the plot that you see there, the plot that you see here, it's still, I call that a pepper and salt plot. So everything is together. You cannot explain, you don't see structure in there. So let's apply some data machine learning to find structure in this data. What can we do in machine learning? Well, we have to do 2 things. We take our data and we have to do 2 jobs, dimension reduction and clustering. Dimension reduction means that for every row in our data, we will make 2 numbers. One says what is the position of the row on the x-axis, and another is what is the position on the y-axis. And the other task that we have to do is do clustering. That means that for every line in our table, we have to assign a color. We have to assign a group color. If you have added those 3 columns to our data, the x-axis areas and the color, you can make a graph like this. And if you apply this technique, like almost every data scientist has done, on the iris set, then you get nice 3 blobs according to the color, and you discover the structure in your data. Unfortunately, in real life, if you apply this technique to real life, it's never that easy as with the iris data set. So let's apply this technique to the wine data set. And I will start with dimension reduction. How does dimension reduction works? Here we have a 3D, it was interactive, but I can't show it anymore, a 3D version of the T-Rex. And suppose you dig up all the bones of the T-Rex and they ask you, put all those bones on the table and put the bones which are close together in the skeleton of the T-Rex, put them close together on the table. How would you do that? Well, in fact, there are a lot of techniques for doing that. Here you see an overview. The most well-known is the principal component analysis, which tries to increase the variance among the axes. People are fond, the Disney is the new kid in the town, which is quite popular. And then unifold mapping and IVIS is the latest one, which is using neural networks encoders to make the best encoding possible. There is a cool video about this, which I will try to show now. It's here. So here you see how the original positions is being optimized such that the transformation, the mapping of the 2D is as optimal as possible. So there are a lot of techniques. I won't go further into detail. For the talk of today, I will focus on the classical PCA and the principal component analysis. Okay. So if you do principal component analysis, the first thing you do is to look how many variation each extra dimension you add explains the data. And I also made an interactive graph of that, which is here. So if I go over here, I can see that with one dimension, I can explain 29% of the variation. If I add another dimension, so if I have 2 dimensions, I explain 44%. And then you see by adding more and more dimensions, you arrive at the 10 dimension at 100%. Here we see that by just using 2 dimensions, we can already explain 44% of the variation. So if we do that and we plot our 5,000 wines, so each dot here is a wine, and instead of using the 10 dimensions, the 11 dimensions, we only use the 2, we get this graph, which is not a lot of better, because we still have pepper and salt, so we don't see structure in there, but we only use those 2 axes to later explain our clustering results. So therefore, we need to understand what is in that first component and what is in the second component. Therefore, you can make nice graphs with the loadings of your principal components. So here we have the first component, and there we see that if the lower the amount of alcohol, the more you go to the right. So the higher the alcohol, the more your point is moving to the left. The lower the alcohol, it's vice versa. That's the problem with PCA. You can't dictate the signs. But the first axis has a lot to do with alcohol, and the alcohol is opposite for all the others. The second axis here, we see here we have 2 strong loadings on the acidity. So the second axis probably has something to do with the acidity of the wine. And so if the lower the acidity, the higher the dot will be, and the higher the acidity, the lower the dot will be. But that's a classical thing that you do when doing principal component analysis. The nice thing, of course, is that you can use the Viridis data set to explain, and then you can hover and you can see all the loadings interactively in Altair. Okay. So now that I have explained the dimension reduction, which is we solely used for the purpose of visualizing our clustering result, now I will talk a bit about the clustering. There are a lot of clustering techniques. Here is an overview of all the sklearn clustering techniques available. With you see the timings, you see the clustering results. Discussing all those would go too far. I just took the most simple one, which was the k-means, for didactical purposes. And the next step that you have to do is to determine the number of clusters. What you do is that you make a clustering with all kinds of number of clusters. So you start with 2 clusters and you increase to 10, and you calculate measures. And here I display the Davis-Baldwin score and the silhouette score. And then based on those graphs, you need some human insight to decide the amount of clusters that you will need. Here we see that the Davis-Baldwin score goes up at 3, and then stables if you add more clusters. So this indicates already that 3. And if you look to the silhouette score, you see that it lowers. So the Baldwin score, Davis-Baldwin score must be as high as possible, and the silhouette score must be as low as possible. You see that you decrease the silhouette score a lot if you go from 2 to 3 clusters, but then the incremental added value is small. Based on this analysis, here we decide that we will go for 3 clusters. Later, after I made those exercises, I found a tutorial here, the link is here. I will provide the slides hereafter. There's a tutorial on Kaggle. If you look there, it's an R. You will see that those people also obtained the same amount of clusters. So I must have done something right. This is the result of our clustering. So we use our dimension reduction here, or 2 dimensions, to put every wine in 2 dimensions. And we use the color to show the result of the clustering. And we see that we have a red, a green, and a blue one. Still, it's okay. And most people think that the job as data scientist is done now, and they go to business and they say, okay, there are 3 clusters and these are the results. Then business start to ask questions. So wait a minute, we are not done with this. We can go further. And this is the new cool stuff I will tell about today. The first thing that I want to show is that with Altair, it's very easy to make an interactively explore these data sets. And I will again show a demo. So I go here, and so this is the clustering. This is the result of the clustering, and here I have my result of my clustering. I can hover over all the dots, and I see for every dot, I see the underlying dimensions, what are the values, so I can already intersect. But the cool thing now is that I can do a brush selection. So for instance, I will do like this. Now only the blue lines are selected and the gray ones are not selected. And I don't know whether you noticed, but the box plots from those lines which are blue are automatically updated. And now I can do a cool thing. I can move the selection thing to the left, and I see instantly all those box plots being updated. And for instance, remember that I said that the first dimension has to do with alcohol. So if we have these lines, we see that alcohol here is the median value is minus 1.2. So, and what happens if we move select wines to the left, we see that the alcohol goes up dramatically. So wines to the left are wines with a high amount of alcohol, wines to the right are wines with a low amount of alcohol. And then the second dimension, I make a brush selection like this. Then we have to look to acidity. If we look here to fixed acidity, the median is 2.5, and now, which is high, and now I go up, and you see what's happening is that the acidity goes even negative. So that's the second dimension we have here. Now, this is very cool for data scientists, but still, yeah, if I go with this plot to my business, they will see all our box plots moving around, and they say, but yeah, no, we don't know which wines we have to promote, or we don't know how to do marketing for these groups of wines. Can't you do it better? Well, okay, we can. What I then do is the following. I train a classifier on the result of my clustering, and I try to, from that classifier, I can derive SHAP values. SHAP values are a game theoretic framework to calculate the strength of the impact of one feature on your model in the presence of other features. So it's not a univariate, it's not one feature on its own, it's the ensemble of features that have impact. What I mean is, I compare it often to the strength of a football team. The quality of your model is the strength of your football team, and the features are players. And for instance, density here is the Ronaldo of our football team. Whatever you do, whatever other features you include or exclude from your model, density is always very important to decide to determine whether you're in the blue, the red, or the green ones. We can also calculate those SHAP values per cluster. So here you see the SHAP values, so the importance of the features which determine whether a wine belongs to the first cluster or not. And here we see that the first cluster, density is the most important, and what you see is that, here you see the color legend, the higher the value, the more red it is, the lower the value, the more blue it is. And here on the ground, you see the impact on the model output. How certain are you that a wine belongs to a certain cluster? And here you see the higher the value of the density, the more the chance is that that the wine belongs to the cluster 0. So cluster 0 can be described as a group of wines which has high density, which has high sulfur dioxide, and which have high free sulfur dioxide. So these are the wines belonging to cluster 0. Here is the cluster 0. So you see here that, and here you see that the box plots are ordered in the same order as the feature importance that you see here. So you immediately see here that the density is the most important feature describing this, this cluster. So we can do the same for the second cluster. The second cluster is then wines with a high pH, low acidity, low density, low citric acid, and high on sulfates. We get this cluster. And then the third one is high fixed on acidity, low pH, and low density. And this reasoning you can easily make by applying the Shapley value. If you apply, so if you talk then to your clients, which has domain knowledge about this, he will understand what your clusters mean. And I find this a very cool technique to do that. Okay. So to wrap up, I explained to here how you make clusters to explain your clusters to business. I extend the state-of-the-art dimension reduction plus clustering by showing that with interactive visualizations, you really can explore your data very, very, very easily. And it's very easy to make visualizations in Altair, and that you can use those game theoretic SHAP values to explain your clusters. All the code I used here to make this presentation, you can find in a notebook on my blog. So all the code is free of use. So if you want to apply this, you can do it for myself. And what is even more cool is my blog has been made with fast pages. There is a button on the top of that blog post. If you click on the Colab button, it will open the notebook, and all this code you see here will run in your browser for one click for free, and you can just change the URL, bring in your data, and run it for your own, and use it for your own good. I forgot to mention that I would talk about the Millennium Falcon, so it's a bit awkward, but I still want to talk about the Millennium Falcon just to have something cool to tell about. Next to the dimension reduction of a T-Rex, somebody did dimension reduction on a Falcon Millennium and Lego. Here is the Millennium Falcon and Lego. It's a 7,000 pieces of 8,500 pieces Lego Millennium Falcon. How cool is that? It costs about 700 euros. And it needs a special trained neural network that is between the ears of some strange guy to make a dimension reduction like this. So here you see all the pieces flat in 2 dimensions, grouped together. And on this bombshell, I would like to conclude this talk, and thank you for your attention.
Thank you. Thank you very much, Lode. I'm sure there will be some questions, and Chris will browse through the YouTube channel for that. But I want to start with an apology, because I noticed that your name is actually Nachtorgale and not Nachtegale.
Yeah, that's story of my life, happens all the time.
Yeah, well, we have an excuse, because, well, we are sometimes, people are saying that we are too much R-minded, and so we decided to take the R out of your name. Look up for that. So that's our excuse. But I also have another question, which actually relates to the dimension reduction thing you showed on the skeleton one. Mm-hmm. So the one in the beginning, I don't know whether you can go back to that.
Yes, I can.
That animation. Mm-hmm. And I was intrigued by the fact that the TSNE one is the only one where at the end all the colors are mixed up. And I was not quite sure how I should interpret that, because in my experience, TSNE is, well, at least in market research type of applications, is doing very well, much better than some of the others. So how should I interpret the last part of the last screen of your animation?
Well, it's just a comparison of what each technique does at this problem, and it shows its advantages and the disadvantages. TSNE has one of the advantages of TSNE. It's very popular. Whatever you throw at it, something comes out of it, but it's often very hard to interpret. You can also not guarantee that parts which are close together in your real n-dimensional data set ends up close together in your visualization. So it can be in Disney that two parts of your tail, which really belongs together because they belong to the tail, they are pink, that due to the algorithm that Disney, it's a stochastic algorithm, it can be that they will be tiered apart very, very much. This is controlled by a parameter called perplexity. You get a lot of nice visualization with Disney, but no one knows, well, it's black art how to tune the perplexity. And then if you have something, it's often very difficult to explain why things are close together. So uniform manifold UMAP is a mathematically much more worked out, and it guarantees you that parts which are close together in the n-dimensional space are as close as possible together in the two-dimensional space. IVIS claims to be the new kid in the town. It's much more compute intensive, but it claims to even better. I myself, I always use UMAP. I didn't have used IVIS yet. But I don't use Disney anymore because it just makes nice graph. Also, UMAP has not only a forward transformation but also backward. You can do inverse, so you can learn from that, which is something which is lacking from Disney.
That's interesting, and I will definitely have a look at this IVIS thing. But my experience with TSNE is okay. I agree with you that the perplexity parameter is perplexing, let's say, but I found the clusters that I found, or the solutions that I found, and let's say were, in my experience, quite well explainable. So it's interesting to see that you have a different experience. So. Chris, do we have questions?
Yeah, we have two. I'll read the first one without understanding a word, but I hope Lode understands a word. So here it goes. It says, "Hi Lode, this is Ismail Persa. Did you try rotated principal components, also known as factor analysis, on your data? Factor analysis redistributes the variance and usually results in a more meaningful grouping of features."
Yeah, the remark is quite well. Thank you, Ismail, for remarking this. Yes, you can. You know, I have to admit that the signs of my PCAs were not as good as it could be, and you can solve that by rotating. So you can rotate. You can combine your rotation with the PCA. You can do that. I did not try it because this was not the purpose of this talk. I needed some dimension reduction and I needed some clustering, indeed, rotating factors with PCA would be also fit in this overview of dimension reduction techniques, but it's just one of the techniques, and I didn't want to discuss about all the techniques and compare them, and you can still visualize the result of your rotated PCA with factor analysis. You can still visualize it nice with Altair. So it was not the focus of this, but it's indeed a good suggestion in this case to use a factor rotation to avoid that something which is high is going down, and which something or going to the left instead of to the right, because most people expect it otherwise. And so for explanation, it will be definitely a better choice. So good remark. Thank you, Ismail.
All right, cool. And then the second question is from Wim Beussaert. And he asked, can you use Altair to make interactive 3D plots whereby you can look at your clusters from different angles?
Currently, I don't think you can do 3D with your clusters. You have to use Plotly for doing that, but Altair is progressing very quick. So it might be in the future that if you're willing to do so, you can contribute. It's an open source project. You can write something yourself. But for the moment, 3D is not very well worked out with Altair and Vega, and in fact it's Vega. So I would recommend using Plotly if you want to do that. However, if you have to explain to business, I would not recommend using 3D. I would maybe use it for own inspection of your data, but if you're gonna present 3D to business, you will confuse them because people are not able to think 3D. Only special kind of people are able to do that. So I would not advise to use 3D to present to your customers.
All right, cool. Well, there's no further questions here, but there are quite a few people who say, really nice job, Lode. Thank you very much. Nice talk. So it's much appreciated.
Thank you
still, Chris, I might still have a question.
Go for it. Yeah.
For Lode. Lode, nice talk. Just two questions, but quite short. The first one is, why did you go through dimension reduction and not directly through, let's say, a hierarchical cluster analysis?
Okay. As I was trying to explain, is that dimension reduction is here only for the purpose of visualization. In the end, you want to go with the drawing to your business and say, oh, these are the clusters, and you want to see structure in there. You could use the output of the dimension reduction. Some people do that, is that you take the output of the dimension reduction and you feed it as a feature to your clustering. And then, yes, for your, that's the first part. I bothered with dimension reduction for the purpose of visualization. I think you need to make some drawing, otherwise you cannot explain. And for the suggestion of hierarchical clustering, yes, it's definitely, is it in here, the hierarchical clustering? Well, the density-based can, the hierarchical clustering is not in here, but it's also, there are libraries available in the sklearn ecosystem for doing a fast cluster is the one that I would recommend to do a hierarchical density-based clustering. And that would be another option amongst all those options you see here. But again,
often the provides a very nice visualization, I think. So you can build a tree or a kind of constellation plot, which is often very nice to present to business as well.
Okay, thank you for your suggestion.
Just out of curiosity alone, just because you say like explaining things to business, how did you explain that quality was the lowest predictive or the lowest important factor in your clustering? So one of your factors was quality of the wines, and you saw that it's lowest importance in the whole clustering exercise.
Now, for the good understanding, this is just a toy example to illustrate the techniques. I cannot discuss things I do within Colruyt because we treat our data very privately, and so I can't share any insights there. But I use those techniques to explain to the business that I do. Here, I didn't. What I did is I did an unsupervised problem. I did not try to predict the quality of the wine. I just took the 11 chemical features of each wine bottle to group them together. And I did not predict anything about the quality. Well, actually, I tried for the sake of, on my blog post, if you go here at the end, here you see the density of the three clusters, the red, the blue, and the orange ones, and the value of the quality. And here you see that in the three clusters, the quality is evenly distributed. But that was not the purpose of the exercise. That's if you want to predict the quality of the wine based on, then you're doing a supervised thing, and that's another talk. And that's not something I want to do.
That's true. But just unsupervised was the quality of the three clusters is kind of the same. That's what you're saying here.
The quality of the clusters unsupervised, you measure with those. So what I do is that I have a big loop that I range over the number of clusters, and I try two clusters, and then I look to the silhouette score and the Davis Balding score, and then I plot the elbow method, and then I see here, okay, the k-mean score. Yeah, the more clusters I do, the lower it is, so it doesn't help. So I tried then the silhouette score, and then I saw, okay, it's lowest, that the biggest drop is 3. So the quality of the clusters is here calculated from the scores.
I see. Thank you.
Okay. Thank you for your question, Bart. Awesome talk to you.
Thank you. Thank you, Lode, and thank you, Tom, and thank you, Bart, for those 3 excellent presentations. Also, thank you, Chris, for taking care of all the technical things, because doing such a live stream is much more complicated than a normal physical meeting. And I also want to thank all the attendees on YouTube for being with us for those 2 hours. And remember that the next Data Science Leuven will be on the 12th of May. So put that in your agenda, and chances are that you will have nothing else to do on that day. So we'll meet again. Thank you.
Thank you, Istvan. Bye.